Hi, I'm Kathleen Coleman, and today I'll be going over Physics 2212, Lab 2, about line charges. I'll begin with an introduction, where I'll go over the purpose of the lab, the physics concepts used, the main results, and the assumptions I had to make, and then I'll go into the GlowScript model, where I'll do a Lab 1 recap, I'll discuss the code, and then look at the results, and then I'll do the discussion and questions. The purpose of this lab was to create a computational model of two charged tapes exerting an electric force on each other, and use this model to estimate the amount of charge on each tape necessary to float one above the other. Really, this is an expansion on Lab 1, except we should get more precise results this time because we're going to be using a better approximation. So in this lab, we needed to understand Newton's second law, which says that net force equals mass times acceleration. Also Newton's third law, which says that every action has an equal and opposite reaction. We should also understand the electric field of a point charge, which says that the electric field is equal to k times the charge over r squared times r hat. The force, which is the charge times the electric field, and then the superposition principle, which says that at a point, the net electric field can be found by summing up the individual electric fields at that point. In Lab 1, I found that the charge on the tape was 9.3 times 10 to the negative 9th coulombs. With the updated model, I ended up finding that the charge was 237% of that, which is 2.2 times 10 to the negative 8th coulombs. And also, once again, the magnitude of the force of gravity will have to be equal to the magnitude of the electric force. The assumptions are as follows. You have to ignore air resistance. You have to assume that each U-tape has the same charge. The charge of each U-tape has to be evenly distributed across its length. Each U-tape can be separated into segments of equal charge, and then that the total charge on each U-tape is the sum of the charges of the segment. Here are my experimental results from Lab 1, and then here is the resulting output from GlowScript. We have the upper tape being the system and the lower tape being the surroundings as well as everything else. And this gave me that the charge on each piece of tape is 9.3 times 10 to the negative 9th coulombs. Now I'm going to go over some of the more important parts of the code. So I began by defining my constants and putting in my Lab 1 data, and then I set Q to be what I found it to be in Lab 1. However, I end up changing this to make it so that the magnitude of the electric force is equal to the magnitude of the force of gravity. On this page, I defined my electric field function, and this is also where the line of charge function is defined. Here, I created the top and bottom tape objects, and this also shows the nested for loops, which demonstrate superposition. Here is the visual output from the GlowScript model. So we have a force upward, the electric force in yellow, a force downward, the gravitational force in green. The orange arrows are the electric field with N equals 50. The red dots, which are kind of covered up by the orange arrows, the red dots are the top tape, which is the system, and then the blue dots are the bottom tape, the surroundings. So this told me that my Q value was 2.2 times 10 to the negative 8th coulombs. So that's the charge that gives us an electric force that balances out the force of gravity. And this is over double the value of Q that I found in Lab 1. So what if you had modeled each of your tapes as a single point charge like in the previous labs? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So when I used the point charge model, I got 2.3 times 10 to the negative 9th coulombs, and with the line charge model, I got 2.2 times 10 to the negative 8 coulombs. So it's a pretty big difference. With the line charge model, the Q was over double that of the point charge model. So why do these estimates differ? And which is likely to be closer to the real value and why? And these estimates differ just because they use different levels of precision. So the line charge model is more likely to be closer to the real value because it uses smaller step sizes, so it does a better job of modeling what's actually happening in real life.